All right, today we are going to be covering Chapter 2 over one-dimensional kinematics. This is going to be a concept-only lecture, and it will not really include much problem solving. That will come in the next video. So there are a few big ideas that I want y'all to take away from this. It's in relation to coordinate systems, velocity, acceleration, speed as it relates to velocity and acceleration, the equations of motion, and free fall. So by the end of this lecture, these are the ideas you should have taken away, and you should have a solid grasp of these 6 concepts. Okay, here I've just included a few vocabulary terms you're going to want to know. So please make sure you really understand the concepts behind these, because we're going to be working problems here in the next video. So let's start with something that we're going to need for many physics problems. We're going to need a coordinate system. And these systems are just used to describe the position of some point or some object. Well, we're going to need to choose the appropriate type before we begin a problem. So that'll either be Cartesian, polar, or spherical, though for most of this course, we're going to be working with the Cartesian coordinate system. Anytime you draw one of these coordinate systems, you need to have 3 things: an origin, you need to have axes with scales and labels, and you need to have an arrow to show direction. Now, it doesn't matter what way you choose to show your positive direction and your negative direction, but you need to make sure you are consistent throughout the entire problem. All right, so position is just where a particle or an object is located. It's going to be a vector or an arrow that points from the origin in the direction that we want to go. So whatever direction that particle or body is moving. Here, you can see that position is going to be represented by x. So x sub f is just our final position, and if you see sub I, it is the initial position. Now that brings us to distance, which is the length of a trip. We're going to measure distance in meters, and it is scalar because it does not indicate a direction. It only tells us a value, a magnitude. And distance is represented by d. Displacement is another term you're going to need to be familiar with, and it is represented by delta x. So displacement is just a change in the position of an object or particle. And that change is calculated by subtracting the initial position from the final position. So xf minus xi. So displacement just tells us the change in position, and it is measured in meters. And it is a vector because it indicates a direction. Okay, so let's take a moment to consider this question. Is it possible to take a trip in which the distance covered is less than the magnitude of the displacement? And on the other hand, is it possible to take a trip in which the distance covered is greater than the magnitude of the displacement? So go ahead and use this image, and I want you to pause the video to think about your response and hit play when you're ready. And if you really just don't know what to do here, go ahead and keep watching. Okay, so let's consider an example. You start here at your house and you go to the grocery store, all right? That is 4.3 miles. You have traveled 4.3 miles and your distance is 4.3 miles. Well, we know that displacement is the final position minus the initial position. So if your house is here, we're going to call this point 0. Then our displacement would be 4.3 minus 0. Okay, so the displacement is 4.3 and the distance is 4.3. So they are equal in that case. Now, let's say you actually return home from the grocery store. Okay, so we saw in that case that distance and displacement were the same. They had the same value. Okay, so now let's say you go here and you actually return back home. So you've traveled 4.3 miles in one direction and you traveled 4.3 miles back. So your total distance traveled is 8.6 miles. And that is a difficult to read 8. Okay, well, what is your total displacement? Well, we started here at 0 and we ended back at 0, which means our total displacement is 0. So in this case, distance is 8.6 and displacement is 0. So this tells us a couple of things. Is it possible to take a trip in which the distance covered is less than the magnitude of the displacement? No, it is not. But is it possible to take a trip in which the distance covered is greater than the displacement? Yes, it is. So the magnitude of displacement will always be less than or equal to the distance traveled. Okay. Go ahead and take that away. Okay. This brings us to average speed. Speed is a scalar quantity. It does not tell us a direction. It simply tells us how quickly a person is traveling over some period of time. And we calculate the average speed by dividing distance and time. And this is measured in meters per second. Distance is a positive value and time is a positive value. So speed can only be a positive number. We cannot have a negative speed. Another concept question. All right, so this time we are going to consider that you are driving 4 miles at 30 miles an hour, and then you drive another 4 miles at 50 miles per hour. Okay, so we want to know if your average speed for the 8-mile trip is greater than, less than, or equal to 40 miles an hour. And then what is the best explanation for that prediction? So again, pause the video if you are not sure here. Well, so that you can try this for yourself. And if you're not sure, just keep listening, but unpause the video when you are ready. Okay. So let's go ahead and plug in our information. We know that speed is distance over time. Well, let's plug in our information for the first one. Okay, so we knew that the speed was 30 miles per hour. And we knew that the distance traveled was 4 miles. We do not know the time, but we can find it. Okay, so when you rearrange this, you find that time equals 0.133 hours, which is approximately 8 minutes. Okay, so let's do this for the other one. Well, we're traveling at 50 miles an hour, and we still traveled the same distance, so 4 miles. Well, how much time did we spend traveling at 50 miles an hour? We rearrange and we find that t is equal to 0.08 hours approximately, which is about 5 minutes. So we can see through these calculations, and I'm not using significant figures or anything like that right now. I'm just calculating this quickly to try to understand the problem. We spent less time traveling at 50 miles an hour than we did traveling at 30 miles an hour. So since we spent more time traveling at 30 miles an hour, that means our average should be closer to 30. Okay. And we'll go ahead and erase that. So if we look at the options here, well, it wasn't split equally. We do not go farther. We go 4 miles each time. And the final answer is that we spend more time traveling at 30 miles an hour. So our average speed must be less than 40. Okay. Now we move on to average velocity. And velocity is a vector, so this time we're going to know the direction and the magnitude. It is measured in meters per second, but it is a lot more useful than speed because it tells us a direction. And we are able to find the average velocity by taking our displacement and dividing it by our change in time. Let's look at a graphical representation of velocity. And here you can see that I have shown this particle's movement in two different ways. So here it's on a coordinate plane. We see that the particle started at this point, moved in the positive direction for 2 seconds, and then started moving in the negative direction. And this arrow told us that. And over here, we've done it on an X versus T graph, a position versus time graph. So these are two different ways that you can show an object or particle's movement, and you will need to be familiar with both of them. Okay, so now let's take a look at the next type, which is, okay, so we're going to take a closer look at the X versus T graph. And on this graph, the average velocity is just equal to the slope. So you'll choose 2 points, for example, point A and point B, and you'll draw your line. And when you calculate the slope of that, it will be equal to your average velocity. So we know what our points are. We see time down here. We see position over here. And you can use that to do delta X over delta T. Two things to take note of are that slope is going to be positive if the displacement is greater than 0, but slope will be negative if your displacement is less than 0. Okay, instantaneous velocity can be positive, negative, or it can be 0. And this is also a vector. It tells us direction as well. And like average velocity is measured in meters per second. The only difference between this and average velocity is that we're simply looking at a particular point in time, and we want to know the velocity at that specific point in time. The instantaneous velocity can also be seen on an X versus T graph, and it is going to be the slope of the tangent. So you'll pick a point, and in this case, we picked a point right there, and then drew our line. And the slope of this line tells us our instantaneous velocity at that particular point. Let me erase that. Okay, go back. So acceleration it's just how velocity changes with time. And an object is going to accelerate anytime its velocity changes. It does not matter what that change is. If the velocity is changing, then the object will be accelerating. Okay, so average acceleration, again, can be positive, negative, or 0. It is a vector. It tells us direction and gives us a value, so it has magnitude and direction. And we find it by looking at the change in velocity over the change in time. And this is going to be measured in meters per second squared. So it's our velocity units divided by our time units. Meter per second divided by second is a meter per second squared. Instantaneous acceleration, like instantaneous velocity, is just the acceleration that we find at some given point in time. So we're going to make that delta t approach zero so that it's really, really small. And at that particular instant, we want to know the acceleration. So anytime the text or I'm talking about acceleration, I am referring to instantaneous acceleration, not average acceleration. And something to make note of is that anytime acceleration is constant, the instantaneous and average accelerations will be the same. Please take note of that. So let's look at acceleration on a graph, just like we did with velocity. And on a velocity versus time graph, so not a position versus time, velocity versus time graph, the constant acceleration value is going to be equal to the slope. So we can see the slopes over here. We pick 2 points and we find the slope. The instantaneous acceleration is the slope of a tangent line at some point in time. So here, 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 wherever we choose, you just draw the tangent line, and that will be the instantaneous acceleration. So when we're talking about acceleration and velocity together and how that relates to speed, if the speed is increasing, that means that acceleration and velocity are going to be in the same direction. Whether it's positive or negative, it doesn't matter. The speed will be increasing. And if the speed is decreasing, we know that acceleration and velocity are moving in opposite directions. So this will be very beneficial when you start drawing your little illustrations. Look out for those key words. If speed is increasing, acceleration and velocity are in the same direction. If it is decreasing, they are in opposite directions. Okay, so this brings us to constant acceleration. And when acceleration is constant, and we said this earlier, the instantaneous acceleration, or just acceleration, is equal to our average acceleration. We can represent that like this. So our average acceleration is equal to our instantaneous acceleration. And that's equal to delta V, or V final minus V initial, over delta T, T final minus T initial. The initial and final times, well, we can just choose those arbitrarily. It really doesn't matter. So let's make the initial time 0. And let's just say that our final time is some time T. So we're going to replace TF and TI with T and 0. So T minus 0. And we're going to do something similar for our velocities. So our final velocity will just be some velocity. So we're just going to call that V. And our initial velocity, we're going to replace that with V naught, which is a way that we represent initial velocity. When we rearrange this, we find that V minus V naught is equal to A multiplied by T minus 0, which that would just go down to AT. So V minus V naught equals AT. And that gives us our first equation of motion. V equals V naught plus AT. I'm not going to take you through the derivations for these next equations of motion. The book does that, so you can refer to the book if you would like to see how these were derived. But these are 5 more equations of motion. So we see position as a function of velocity and time. We see our constant acceleration equation for average velocity. Then we see one for velocity in terms of displacement, one for position as a function of time, and position as a function of both time and acceleration. So you don't have to commit these to memory, though you might start to remember them the more we work with them. They will be provided to you on tests and quizzes. So please do not spend a lot of time trying to memorize these. And here they are again in a nicer form all together. So you can see what variables are related and the equation. And this is the number in the book. So this is equation 2.7. We see equation 2.9. So that's what they're referring to when you see 2.7, 2.9, 2.11, whatever it may be. Lastly, we're going to talk about free fall. So whenever we release an object, whether we are throwing it into the air, or dropping it from rest, or throwing it downward, that object is considered to be in free fall and is being acted upon by gravity, which has a value of 9.81 meters per second squared. And that meter per second squared indicates acceleration. So the moment an object is released, we say it goes into free fall. And that just means it's only being acted upon by the force of gravity. So we are assuming that friction and air resistance are negligible. This is a graphical representation of free fall, and it is a nice parabola. We see that the velocity starts at 0, its midpoint is 0, and it ends at 0. So that is it for this. So at this point, you should have a pretty decent grasp of coordinate systems, velocity, acceleration, speed as it relates to velocity and acceleration, the equations of motion, and free fall. Again, this was just a concept video. Please join me in the next video as we work a few problems. I'll see y'all next time.